I'm Miles Parker. I lead the Eclipse Agent Modeling Platform project, and today I wanted to talk about why we might be interested in modeling the real world, which is essentially what the Agent Modeling Platform is all about. Okay, so why model reality? I think that the easiest and most expressive way to say that is simply that that's what we do. The question is, are we going to do that implicitly? And what are these implicit models? They're the stories we tell ourselves. So they could be anything from all of the assumptions that are made in newspaper articles to the assumptions that we make when we throw a ball in the air and expect it to come back down in a certain way. All of these relate to what we think about the world, how we think the world works. Then there are these explicit models, and these are the ones that we've written down, that we've written down in a formal way. And so, of course, we have business process management and finite element analysis and econometric models and models of disease process and so on. And in the software world, we have requirements analysis and all of the other pieces. What are these about? These are about things we want to make, and things we're afraid are going to happen, so managing risk. What we need to recognize is that all of these models are stories, regardless of whether they're implicit or explicit, and all of them are lies. They're always going to be wrong for some circumstances, and in some perverse way, the universe is going to make sure that they're wrong at exactly the wrong time, or in some cases, they can be wrong in a beautiful, unexpected way. So, why are we interested in stories if they're lies? Because they're useful. But let's not get too confused about that. Why would we want a story? We usually pick them out because one is more helpful than another. And actually, software developers, compared to a lot of scientists and engineers, really deeply understand that. And that's because we deal with people every day. And because we have, before the Agile movement, we have 30, 40 years of records of failures in pretending that our stories are reality. How do we differentiate different problems with stories? What are the different kinds of problems with stories? Well, there's the obvious one, which is simply that we have biases. We have political views, for example. We might have used a tool and not used another one, and so we like the tool we've used or the tool we've been involved in building. A deeper aspect is retrospective thinking. Every one of our stories is about something that has already happened. And so even if we're guessing about something that's happening in the future, it's always going to be retrospective. A somewhat deeper level is that our thinking becomes constrained by the problem itself. So if we think about designing a nuclear reactor, when we design a nuclear reactor, we may be thinking that the problem is that radioactivity escaping the reactor core itself. So that's a reasonable thing to think. So we build all these layers of protection around it. Well, that may not be the best way to make a nuclear reactor safe. And even if we do that well, we may not have made the reactor safe. And then finally, at the deepest level, there are all these human biases just in the way we think. And there's a really significant literature in experimental psychology, and people in the intelligence community have discussed this quite a bit. But we have issues like confirmation bias, where we literally see the things that we expect to see. So what do we do about this? Well, let's just make better stories. And how do we do that? We collect more knowledge. This is, of course, what humans do best, right? And this is what people think about often when they think about science, is going out and collecting more specimens and so on. Then we need to put all of this together, and that's easy. We'll just kind of put data dictionaries together and and connect all of the different pieces. And then finally we can process all that and we can make inferences about it and we can figure things out automatically. That would be cool. These are all better lies. And in fact, the more stuff we get, the bigger our lies and the harder it gets not to tell lies. Let's look at big data, which is the big thing right now. And here the idea is we'll collect all of this information and then we'll go and do whatever we want because we've got all the information that basically explains everything that happens in the world. The problem is, of course, that data doesn't explain everything in the world. It doesn't even contain everything in the world. It contains what we've collected, and that what we've collected, regardless of how much information we contain, we collect, is a very narrow slice of the information that is actually in the universe. And then what happens is because we have that information, we use that information to try to solve all of our problems. And this creates profound biases in how we approach problems. Then there's the context frame problem, which everybody would like to ignore. And from talking to the sort of software engineer on the street, I'm kind of convinced that some people really aren't even aware of. This is a deep issue that was first really tackled by Gödel and Wittgenstein, but has goes on to Turing and more recent results such as the no free lunch theorem and so on. But basically all these things are about saying there is no one way to coordinate all of the information in the world, or even, I would argue, in any kind of small slice of the world. And yet we continue to pretend that there is. And so that if we collect all this data, all these disparate data sources, that we're going to be able to hook these in and using some sort of magical tool set. The next is that if we look at the way we use big data, it's inherently reductionist, which simply means that we're always sort of gathering this information up and bundling it together, doing statistical analysis on it and so on. So that then almost always when we end up presenting that to people, we're presenting a very filtered view that takes out all of the nuance and deeper sort of complex relationships in that data. And then, of course, there's this issue of retrospective thinking, which is exactly what we're going to get with data. We need that. We need that for any kind of model because it helps us to understand whether the model is correct or not. But on the other hand, when we rely on that, say with financial modelings, for financial models, that's when we really get into trouble. Because everybody else has built their model on the same assumptions, and when things don't match those assumptions, everything falls apart in a very big way. This is why big data is big dumb. So what's the answer to that? Well, we'll get computers, and these computers will take the data and crunch them together, put all the different pieces together, and then reason about them, and then we'll understand how the pieces fit together, and we'll just kind of infer everything, which sounds great. There's some problems with that. In addition to the context frame problem, there's the combinatorial explosion issue, which all software developers are familiar with, which is that almost all interesting problems get into this issue pretty quickly of an expansion of the problem, so that if you think the problem is twice as hard, it actually takes 4 times as much computer power to handle that. If you think if it's again twice as hard, it actually takes 16 times as much computer power to handle it, and so on. And again, we think that we can solve that by massive parallelization and so on, and there are techniques for dealing with that. But people put too much faith in those and what is given up when you go to those kinds of solutions. So people claim that there's this 80-20 rule, and I think that that's actually one of the deeper understandings. And if you look at say IBM Watson and Wolfram Alpha and look at what the people that are building those systems are saying, you get kind of in the 4th, 5th paragraph or so, or further down, into this discussion of the 80-20 rule. And the idea here is that the AI can do a lot of heavy lifting, but when it gets right down to it, there are these pieces that AI just can't handle very well. And I would argue that the 20% is actually the difficult part. because it's the part that involves the deep knowledge and intuition and so on. And so again, what do we see when we look at systems like Wolfram Alpha? We see that ultimately there's a person in there. When you look at something on Wolfram Alpha and you just really go, wow, how did the machine know that? Inevitably, when you dig down into it, you find somebody somewhere has put in the crucial little bit of information that allows that kind of inference to occur. So it's not automatic. It's got humans in the loop, and what are they doing? They're curating. What is curating? It's building models. But ultimately, AI is smart dumb. So how do we get real smart? Well, there are even more issues. We need to get a grip on time and space, and those are issues that aren't dealt with very well in traditional reasoning. And then there's the whole issue of reasoning under uncertainty and soft logic, non-monotonic logic, all of these kinds of things that are deep issues. We're not going to solve them perfectly, but whatever solution we have needs to engage with these. And then deeper is just the issue that the world cannot be separated into different bits that aren't connected to each other. That if we're looking at drug discovery, we can't just throw a bunch of proteins together in an isolated test tube and figure out whether a drug is going to be effective or not. And you can't even apply that to, say, DNA models. You need to understand how people work in social situations, whether they're going to take the drug or not. You need to understand what's going on inside of organ systems at the cellular level and so on. And then you need to understand that these systems are complex and that you can't predict absolutely what's going to happen with the system from one moment to the next, and every system is going to behave differently. Well, what does a real model look like? First of all, these are really all about just creating a shared understanding, and then putting these kind of into a sandbox so that we can look at them together and sort of push the bits around and see how they fit together. See if when you start something running, if that behavior is what you expected or if it's something entirely different. And do that in a collaborative way. The way I like to think about this is that models can create dialogue, and they can also uncover a lot of bullshit. So let's take an example. Here's this kind of dialogue that some of us that have been involved in software working with users are familiar with, where you just go back and forth and you ask questions. So here you can get to this issue of, well, we thought that the probability of the battery going bad was entirely independent of the probability of the diesel generator going bad. But in fact, if one of them, the cause of one of them going bad could very well be the cause of the other one going bad. And we should have discovered that at some point. And as we go through that process, the agent modeling platform, for example, is about running these models, but it's also about just the process of designing these models. And something interesting happens when we start to build these models. Other pieces start to come in, other concerns start to come in, and this is separate. This is very different from the process I described earlier of trying to figure out how to contain a reactor. Because we start to ask deeper, more human questions. And we notice that all of these problems end up involving people, and I think it's fair to say that people are one of the most complicated parts of the universe. Well, how can we model things that are so complicated? There are traditional ways to do this, going back to the Greeks. We have inductive reasoning, which is related to data, generally. Okay, these things have happened, boom, 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 and because all of these things have happened in the same way or in predictably different ways in the past, then this is what we expect to happen next. There's deductive reasoning, and this is probably more associated with AI. You figure things out. Well, this is true, and this is true, so this must be true. And there are all kinds of reasons that sort of reasoning could be suspect. And then there's this third way, and this is something that Josh Epstein proposed, and that probably about 10 years ago, and I think is really underappreciated. It's actually it's a pretty radical and deep suggestion, which is that there's actually a third way of reasoning in the world that is just as about the world, that is just as valid and powerful as these other approaches. And the idea here is you build something, and if it ends up matching what's actually happening in the real world, that's a reason for thinking that you've got a good model, that you've got a decent representation for what's happening in the world. Well, let's put all of these pieces together. And that's actually, in a deeper way, what the agent modeling platform is really about, is trying to figure out ways to take these traditional reasoning approaches and generative reasoning, which seems to be agents running around on a screen and so on, but it's actually much deeper than that, and integrating all of them. Well, we say integrated, and then we think again, gosh, I'm going to have this perfect model that explains everything. No, that's not going to happen. It's not going to be complete either, and guess what? We're not going to be able to tell you what's going to happen next year, and anybody that tells you otherwise is lying to you. But they can be transparent. They can create the situation where we can have this shared picture of how reality works. Yes, it's transient. Yes, it's imperfect. But it's helpful and useful in some ways. And most importantly, it's explanatory. And again, this is another distinction that Josh Epstein makes between prediction and explanation. Prediction can kind of in a very black box sense tell you what's going to happen next. We can't do that with these models actually, and people are always of course asking us to do that. You know, there are pieces that we can do of that, but ultimately we have to say that these systems are too complicated to predict in that way. What we can do is explain how these systems work, what's interesting and beautiful about these systems, and what you might want to look for if you really wanted to understand or engage with these systems. Well, as a software developer, and that's who this presentation was originally designed for, you have this question about why would I care about modeling reality? People hire me to model their particular systems. They've got a particular problem. My job is to solve it. So there's this idea of user stories, which is actually really nice because you're asking the users to tell you what the problem is in very plain language. But at some point you need to put that into a computer system. So you start building up an architecture, and when you do that you say, well, there are more elegant ways I can put all these pieces together, and so let's look at the system more holistically. Let's look at the bigger picture. We could go even further than that, though, and actually really think about the context of how people are interacting. And I think there are beginning to be software tools out there that are doing this, tools like TaskTop that think about how people deal with the huge amount of data that they're faced with, and creative ways to expand and contract the amount of information, to contextualize it, and so on. So you should care as a software developer. And also, a lot of people have a problem with this whole idea of meta-modeling. But you know, you need it. And you need it if you really want to create models that generate things and that are engaged with reality. One thing meta-models let you do is understand what all the assumptions are of the domain. And it's actually more important than the assumptions about the data. It's actually the assumptions about what part of the data is important and how the pieces of the data fit together and so on, in short, with methodology. And then we talk about cross-disciplinary, interdisciplinary stuff and so on. Well, if we're going to get different disciplines, and this is a problem even, say, within the social sciences, trying to get economists and political scientists to talk to each other in in a richer way. But certainly, say, getting political scientists to talk to biologists and so on, we need to actually understand the entire set of assumptions and methodological techniques that people are using, and the only way to do that is to understand their methodology. The thing is, of course, these are all nested because methodologies presume other methodologies and so on. As the famous joke goes, it's turtles all the way down. But there's nothing we can do about that. We're just going to have to face that problem. What's different between modeling reality if you decide that it's something you want to get into versus, or on top of traditional software modeling? Well, to issues of type and behavior, we add scope, which is much deeper than namespace issues and so on. We have many, many dimensions of how these models could fit together, and that's a hard problem to figure out, an interesting problem to figure out how to do that, how to be able to take different slices of behavior that are appropriate to various targeted domains or information spaces. All of this stuff happens in space and time, and the space need not be explicit. It might be social space and so on. Of course, things are not neat at all, and for that reason, really understanding the correctness of our model becomes more important. And more than that, understanding that our models can never be truly correct is critical. But we do want to know that, and we want to be able to demonstrate to others that our models fit with reality better than other approaches, and that their models are defensible. And we need to provide tools to do that, and that's been one of the focuses of the agent modeling platform, actually. Because when it gets down to it, the real value of being able to model reality, or one of the major values, is that it allows us to explore outcomes that we didn't expect. Because in the real world, you can't go back and say with the reactors in Japan, let's have a do-over. We need to be able to model systems in a way that is rich enough that the kinds of things that we didn't expect to have happen can happen in the computer before they happen in the real world. So there are all kinds of different ways of techniques for doing this sort of modeling of reality. My background is in agent-based modeling, which is the newest approach, and really gets down into, let's create individual agents representing all the pieces, give them rules, let them interact with each other, and see what happens. Systems dynamics is an older but quite rich way of modeling complex systems, and we have contributors that are building pieces of that for the agent-based modeling platform, and those will be completely integrated so that you'll be able to build system dynamics combined with an agent-based model. And then there's discrete event simulation, which is very similar in I think most of the important ways to agent-based modeling. And there are all kinds of other analytical approaches. Of course, there are equation models, which are which have a relationship with systems dynamics models. There are regression models, other kinds of statistical models, optimization techniques, and so on. The idea of the agent modeling platform is, let's figure out how to put these all together in an integrated way, and then let's go back and match those up with other kinds of reasoning, and let's take big data and AI and this kind of modeling approach and make all of these different pieces work together. Thanks.